This video contains a solution for AP Physics C 2007 Mechanics number 2. We have here March 1999. Global surveyor entered its final orbit around Mars, sending back data to Earth. Assume a circular orbit with a period of 7.08 times 10 to the third seconds and orbital speed of 3.4 times 10 to the third meters per second. And the mass is 930 kilograms, the radius of Mars 3.43 times 10 to the sixth. And they want part A, calculate the radius of the orbit. Well, let's see what we have here. We know period, 7.08 times 10 to the third seconds, and we also know velocity is 3.4. It's really speed, right? Velocity is a vector and it's going around, but we'll call it velocity anyway. They very carefully said orbital speed, right? Because it's going around in a circle. And they want us to find the radius. Well, the easiest way to get there from here, you could take a few steps and try to get to Kepler's third law, which looks like gm over r cubed. You could go that direction, but I think we're just going to need that later, right? I think here we have, if we have period and velocity, well, the period, or I should say the velocity of something moving in a circle, like in a circular orbit, is 2 pi r divided by how long it takes, right? That's just distance, 1 lap, divided by time, period. So we're just missing the t here. No, sorry, we're missing, well, they want us to find the r, so r would be equal to, let's see, vt over 2 pi. Don't get too excited about that Virginia Tech reference here. It's velocity times time. And that should give us, I'll spare you the calculator work, 3.83 times 10 to the sixth meters. Part B, they want the mass of Mars. I think this is where we get to use Kepler's law here. So solving this for m, that would look like what? The m and the t squared will swap places there. So that's 4 pi squared r cubed over gt squared, right? And that should give us a value of 6.64 times 10 to the 23rd kilograms. I'm going to go ahead and calculate that just to make sure everything is correct. So, you see that okay? No, you can't see that there, can you? Let's try here. So we have 4 pi squared times r, which we just found was 3.83 times 10 to the sixth cubed, divided by, don't forget your parentheses for the, you have more than one thing on the bottom, g, which I think I have stored in this calculator as capital G. Let's find out. Let's see if we get the right answer. G times the period squared, and the period was 7.08 times 10 to the third squared. Oh dear, that's not good. You see what I did there? That's an easy calculator mistake. I'm squaring the g also there. I don't want to do that. So let's put the squared there. That should do it. And that gives me 6.63 times 10 to the 23rd. And that's, well, 1 decimal place different from what they got, but that's just fine. All right. So far, so good. Part C. they want us to calculate the total mechanical energy of the GS in this orbit. Well, you just need to know that total mechanical energy is equal to kinetic plus potential energy. And for orbital situations, remember that the kinetic energy is G m over 2r, and the potential energy is actually minus G m over r. So before we do any work, I mean, you can find those two numbers and subtract them, but that's half as big as this. So if you combine these, do that, you get minus G m over 2r. That's what we're looking for right here. And we should get, let's plug in our values and see what we get here. Can you see that? No. Can you see that? Yeah, that looks good. So we have minus G m, that's our 6.64 times 10 to the 23rd that we just got, the mass of Mars, times the other m, which was 930 kilograms for the global surveyor, divided by, parentheses again on the bottom, 2 times the radius of the orbit, not the radius of Mars, right? It's the orbital radius, which is 3.83 times 10 to the 6th. 3.83 times 10 to the 6th. And let's see what that gives us. Something, let's see, that's G m over 2r, and that answer is not agreeing with their answer. So we'll have to come back to that and see what happened there. They took a little bit different approach there. They used the no, I don't like that. Why did we not get the same answer? It looks like we've done everything right. G, I'm just checking my calculator here. We have G times the mass of Mars times the mass there over 2 times the orbital radius Well, you'll have to check your work there and see if you can get the right answer. Their correct answer is negative 5.38 times 10 to the 9th joules. And I'm getting, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm getting a smaller number by, it looks like a multiple of 3. That doesn't make any sense. No, not quite. So we'll have to try to fix that. Part D. If the global surveyor was to be placed in a lower circular orbit, closer to the surface of Mars, would the new orbital period of the GS be greater than or less than the given period? Well, let's see. Since t squared is directly proportional to r cubed, that means that if we go into a lower orbit, we have a smaller period, right? So that would be less than, and I think our justification would be exactly what we just said. We'd say because t squared is directly proportional to r cubed. So smaller r implies smaller t. And then here, in fact, the orbit that the global surveyor entered was slightly elliptical, with its closest approach to Mars at 3.71 times 10 to the 5th meters above the surface, and its furthest distance at 4.36 times 10 to the 5th meters above the surface. So if the speed of the GS at the closest approach is the speed that they gave us, they want the speed at the furthest point. Now that we know that it's going to be going faster, so we should definitely get a speed that's slower than that. So let's see. The concept we want to use, we saw this in a multiple choice question fairly recently. We want to use conservation of angular momentum, where we treat the surveyor, the global surveyor, like as a particle. So it'd be conservation of angular momentum. So L1 equals L2, however you want to label these. This will be like maybe this could be the closest, and this could be the furthest, right? So that will give me the equation. And remember that angular momentum here is R cross P, right? It's like regular momentum, but it's the cross product with that distance from the center of rotation, which here is the center of Mars. And since we're at a 90-degree angle, the nice thing about the closest and furthest point in an elliptical orbit, those are the two places where you are actually at a 90-degree angle, right, at those points. Everywhere else it's not quite 90 degrees. Might be close, but it's not. So that means this R cross P, which is R M V, so remember, momentum is mass times velocity, sine theta. The sine theta, sine of 90 degrees is just 1, so it's just RMV equals RMV. So RMV, this is the radius at the closest approach, and the velocity at the closest is equal to R at the furthest, and the mass is the same, so that doesn't matter. So that gives us a pretty simple equation here. If you want to know what the velocity is at the furthest approach, it's just the velocity at the closest approach times the radius divided by the radius at the furthest approach. And that should give us an answer of 3.34 times 10 to the 3rd meters per second. Okay, let's go back and see if we can fix that part C. Maybe we misread some information here. An orbital speed. Yes. I guess the thing that we have to take into account in Part E, this is still about Part E now, is they gave us the closest approaches. So with these numbers here, those two radii, you'd have to do this number plus the radius of Mars, right? This is how close it is to the surface of the planet. So you have to add the radius of Mars to that and add the radius of Mars to this to get the proper numbers there. So please don't forget about that. When they give you altitudes, you have to use you have to add in the radius of the planet. All right, so let's see how we're doing. 14 minutes. If we can wrestle with that part C for a moment. Did we use a wrong mass or something like that somewhere? I don't think so, because we have both masses in these equations. Total mechanical energy should be the kinetic energy, GMM over 2R, GMM over R. I'll have to add a note to this video to see what happened there, because I don't want it to be longer than 15 minutes. So back to that later.